จะเป็นการบรรยายเกี่ยวกับการใช้เครื่องเร่งอนุภาคทางด้านการแพทย์นะครับก็คือที่ใส่หน้ากากนี่ก็คือว่าเราเป็นหวัดครับ เราเลยต้องบอกว่าสุขภาพมีความสำคัญกับพวกเรานะครับถ้าเกิดเราไม่สามารถจะทำอะไรได้ถ้าท้องเราหิวหรือสมองเราป่วยนะครับเพราะฉะนั้นสุดท้ายไม่ว่าคุณจะทำอะไรก็ตามถ้าร่างกายไม่แข็งแรงก็ไม่มีประโยชน์นะครับสิ่งหนึ่งที่เราต้องตอบคำถามให้กับtaxpayer หรือคนเสียภาษีให้เรา funding agency ของเราหรือผู้ให้ทุนเรานะครับว่าแล้วสิ่งที่เราทำมันมีประโยชน์อะไรอันหนึ่งก็คือประโยชน์ทางด้านการแพทย์นะครับก็ในช่วงเช้านี้เราก็ได้ผู้เชี่ยวชาญทั้งจากสถาบันวิจัยที่มีชื่อเสียงจากสวิตเซอร์แลนด์นะครับ Scherrer Institut แล้วก็จากโรงพยาบาลจุฬารวมถึงมหาวิทยาลัยเทคโนโลยีสุรนารีในช่วงที่2แล้วก็สถาบันเทคโนโลยีนิวเคลียร์แห่งชาตินะครับซึ่งเป็นช่วงสุดท้ายของช่วงเช้านะครับก็ในช่วงเช้านี้ท่านแรกนะครับก็จะเป็นดร. มาร์ติน กรอสมัน ฮันชินจาก Scherrer Institut หรือ PSI จากสวิตเซอร์แลนด์นะครับแล้วก็หลังจากนี้ผมก็จะขอดำเนินรายการเป็นภาษาอังกฤษนะครับแล้วก็ท่านไหนมีคำถามเป็นภาษาไทยหรือว่าต้องการให้ช่วยทางด้านอธิบายอะไรบางเรื่องก็สามารถถามเป็นภาษาไทยได้นะครับ Okay, ladies and gentlemen, so I would like to switch to English now since we have I think 4 people at least as far as I know. First is Martin, second one is my postdoc there and the from Bangladesh I think is from at least 4 people and I think 1 student I'm not sure Abdul my PhD student so there are 4 foreigners as far as I know if there are more please raise your hand okay no anyway so what I try to say in Thai and now I translate into English is that we are researchers we are particle physicists we are whatever we are but what is the benefit of doing research if this research cannot bring down to the taxpayer? And we cannot answer our funding agency what is the benefit to the society and everyone that contribute to this research, okay? So it is our honor that we have Dr. Martin Grossmann Handschin from Scherrer Institut to be here with us to give the first talk.Sorry, you didn't give me your English title. I'm sorry. The title in Thai is the application of proton accelerator in medical. Is it correct? Okay. Then without further ado, please give the microphone to Martin, please.
Thank you very much for this nice introduction. So this is the official English title. Let me start with showing you a little bit where I'm coming from. PSI, Scherrer Institut, Paul Scherrer was a Swiss physicist, is located in Switzerland, so in the heart of Europe.It's about 1 hour drive from Zurich to get to PSI. But as you can see on this photo, we are really on the countryside. And this is because it started as a spin-off from the 2 big universities in Zurich, ETH and University of Zurich. But in the city of Zurich, there's no space to build such a facility. So this is why the institute was built outside. And we have many accelerators.And you see them here. We have here in this big building, this is how PSI started. Basically, it's a 590 MeV cyclotron for protons, so medium energy, but very high intensity, 2.4 milliampere, which is the world record for a proton cyclotron. And this high proton beam allows us to make secondary beams of pions and muons, and also later neutrons, and we do a lot of research with these secondary particles, both fundamental physics and also applied research. We have a second, smaller cyclotron, 250 MeV, and this is the one which will be in the focus of my later presentation today, because this cyclotron is exclusively used for medical application for the treatment of cancer patients, and I will talk mostly about that. But we have more. We have a synchrotron light source, a bit more than 20 years old, and just now undergoing a major upgrade. They really changed completely the whole accelerator. It's just the building that will be the same. And for 2 years, there will be no beam time, so just now everybody is very busy in this hall. And here in the forest, at the time when this photo was taken, it was still under construction. It's a free electron laser, 700-meter long electron accelerator with FEL, so time structure characteristics. And both the synchrotron light source and the free electron laser, they are doing all this broad range of applications that we heard about yesterday. So, okay. So my talk today, radiotherapy with protons. Radiotherapy uses the fact that radiation is dangerous for biological tissue. If a cell gets too much dose, it will die. This is what we use in normal radiotherapy with electromagnetic radiation. You irradiate a tumor and eliminate the dangerous cells. Now, the difficulty in radiotherapy is not so much to damage the tumor. That's easy. You just irradiate long enough and the tumor will get the dose and it will die. The difficulty is much more to spare the surrounding healthy tissue, the tissue that is in the flight path. And here, particles, and in particular protons, have an advantage over the conventional radiotherapy with electromagnetic radiation. And this is the reason why we do radiotherapy with protons. The price to pay you see on this picture here, this is a conventional LINAC to produce therapeutic gamma or electromagnetic rays. And this is a typical proton facility. You see it's much bigger, very heavy, and this means it's more expensive. And why do we do this? The answer, of course, is in the physics. You have here on this axis the penetration depth of the radiation into the tissue. You have here the dose, which is the effect of the radiation. And the protons have a defined range. They stop at a certain depth. And this is where they create the biggest damage. And if you have a tumor that has an extension in proton range, by changing the proton energy, you can cover the whole target volume with this blue sum curve and get a good coverage of the target. And photons have a completely different behavior. They have most of the effect close to the surface. In the region of the tumor, it's about the same, but what you have to compare are these surfaces. What is the dose outside the tumor? This is the dose that you do not want in case of photons, and in case of protons, it's not zero, but it's much less. And this is the reason why we use protons for radiotherapy. What are the main components of such a treatment facility? You need an accelerator. In many cases, it's a cyclotron, like in this example here. You need beam lines that direct the beam with magnets into certain treatment rooms. And from the treatment rooms, we have two types. This one, which we call fixed beam line, the protons coming out here, you can hardly see the vacuum tube passing through some components that shape the dose. And then the patient seated, for example, on a chair, could also be lying on a patient table. But the beam line is always fixed. And in contrast, you have these machines, which we call gantry. A gantry is a beam line that can rotate around the patient. And this allows us to come with the proton beams from different incident angles. And so in the crossing point of these various beams, you get an enhancement of the dose. This is what we use. This is the cyclotron that we use. It's a commercial one, not built by us. It was built by this company called Accel, which later was bought by Varian. So Accel built the first prototype of this superconducting cyclotron, rather compact, rather service-friendly. And PSI has the first one, the prototype. And this then, when Varian took over this company, this then became the cyclotron that is installed in all the Varian ProBeam systems. And we use it since almost 20 years now, and it's really very reliable. Yeah, you have an inside. You see a person here. So for an accelerator, for cyclotron, it's quite compact. 1000 nanoampere is the maximum current that we can get, and that's more than enough for our therapeutic applications. It must not be a cyclotron. It's also possible to do particle therapy with synchrotrons. This is a facility in the north of Italy next to Milan, which is sort of a spin-off from CERN. The people that have built this facility, they were at CERN before. But you see already the big difference is that you need more space for a synchrotron. And if you think about clinical facilities, space in a hospital is always an issue. So this is why mostly cyclotrons are preferred for proton therapy. This is how the facility at PSI looks today. So we have in one corner the cyclotron that I talked about. We have the different beam lines. And we have 1, 2, 3, 4 treatment rooms. These 3 treatment rooms have been built by us, and they were in several aspects pioneering facilities, and I will talk in more detail about that. And this gantry here is a commercial gantry. It's exactly a Varian ProBeam gantry that we integrated into our facility. And I want to mention one point here. The cyclotron, as you know, gives a fixed energy, but for the clinical application, you need a range of energy. And so you must reduce the energy from the 250 to whatever you need. We go down to 70 MeV clinically. And for this purpose, here in this region, we have a degrader. It's a system of carbon wedges that we can drive into the beamline, and then the protons travel through more or less material. They lose more or less energy, and so we can reduce the energy. And remember this degrader because it will become important towards the end of my talk. But there is also a similar proton therapy just the other side of the road here in Chulalongkorn Hospital. And I had the opportunity earlier this year to visit this facility. So this is exactly the same gantry like the one that we have installed at PSI. Let's talk about how do we shape the dose to give the form of the tumor. We have 2 different possibilities to do it. The classical method works like this. You take the proton beam from the accelerator, let it pass through a scattering foil which broadens the beam. You bring into the beamline a collimator, a piece of metal, for example, that has the form of the tumor cut out, and then you position the patient downstream of this collimator. This collimator has the individual form of the tumor, so it has to be individually produced for each patient. But once you have such a collimator and once you have positioned the patient correctly, it's a relatively simple technique because the only quantity you need to control is the dose. You switch the beam on and switch it off in the right moment. So this is why with this technique, proton therapy started in the 1960s, early 60s. They were all using this technology. PSI started in 1984 as one of the first places in Europe to use protons. And we concentrated on one special indication, the treatment of melanoma in the eye. So you see here the view into the pupil of one of our patients, the background of the eye, and here is a tumor that grows into the eye. These tumors are dangerous. They destroy the eye. But worse is they easily build metastasis in other organs of the body. So if you don't treat such a tumor, the patient risks to get, for example, liver metastasis, and that can be fatal for the patient. So when you discover such a tumor, you have to remove it. And before protons, removing the tumor means you have to remove the eye. Now, most people have two eyes, but if you can keep both eyes, it's a big advantage for the patient. And this is why this indication was sort of a pioneer field for proton therapy, because you have really a big advantage for the patient. We collaborate with ophthalmologists who prepare the patients in an operation. You see the ophthalmologist there, and here this is a model of an eye. It's not a real eye. Under anesthesia, the ophthalmologist pulls the eye a little bit out of the socket and shines with a lamp through the eyeball. And maybe you have seen on the first slide, these tumors are melanoma. So this is skin cancer in the eye, which means these tumors are dark. So they cast a shadow. You can see very clearly where exactly is the tumor. And then the position of this tumor is marked by stitching very small metal clips onto the eye. We use tantalum, which is a good biocompatible metal, and they are very small. And then the eye is put back into the socket. And it sounds very dramatic, but our eyes can move very well, so the patients can tolerate it quite well. But it's invasive. A couple of days later, the patient comes to PSI. We prepare face masks, which adapt to the form of the skull. The patient has a bite block in the mouth, so you really cannot move the head anymore. And then this mask is fixed to the treatment chair, so the patient is fixed. And then we rotate the patient in the direction of the beam line here. And this is what you see in the next picture. The beam coming from here. Here in this position is the collimator. And we do not yet switch on the proton beam, but we take X-rays. And on this X-rays, you cannot see the tumor. It's transparent for X-rays. But you see these metal clips from this surgery. And you compare here in color, this is the nominal position, and you see the shadow where these clips actually are. So in this photo, the patient is a few millimeters too low. The chair is connected to an hexapod industry robot, so we can correct the position, lift the patient, take another X-ray until the position is fine. And then we do the irradiation. In the case of these eye tumors, we have only 4 sessions, 4 fractions, where we give quite a lot of dose in one fraction, 16 gray, so that we reach a bit more than 60 gray after 4 sessions. It's quite a lot of dose from the point of view of radiobiology, but the result is extremely good. We have treated now, I should update this number, but by now it's more than 9,000 patients. And the success rate is really good. 98%. Cure, meaning here 5-year local tumor control. This is the quantity, so it's really working very well. No danger of metastasis, tumors not growing anymore. And also important, in most cases, we can conserve the vision of the patient. The patients can see as well as before the treatment. So for this kind of tumors, protons have become a standard. So it's really a very, very successful therapy. Motivated by this success, PSI in the late 1980s decided to expand the proton therapy program to also treat other kind of tumors, not only these eye tumors, and use a completely different irradiation technique, which we at that time called spot scanning. Nowadays it's more called pencil beam scanning. And here is how this works. We take again the proton beam from the accelerator, but we leave it focused, and use the fact that the magnet can change the direction of the proton beam. So we set the proton beam, we set the magnet for a certain value, and then switch on the beam, set one dose point, switch off the beam, change the magnetic field. You see, we scan one line in the target volume. And now something here happens. We bring material into the beam line and then repeat the scanning. And this material means that the protons lose a little bit of energy, which means they don't reach that far in the patient. And we get a second line, but a bit more proximal. And now it's clear how this continues. You can change the energy again, adapt the range of the scanning field. So with this technique, it's possible to cover three-dimensional volumes inside the patient without the need for patient-specific hardware. You don't need collimators here. But it's more complicated. You need to control the dose, but you also need to control the position and check the position. So the idea to do this is already quite old, but you had to wait until the 1980s when the technology was there. You need fast power supplies for the magnets. You need fast control of the beam. You need fast analysis of the beam profile to check the position. And all this is applied particle physics. It became available in the 80s, and the team that had the idea to build this at PSI, they were particle physicists, but they knew how to do this. And they teamed up with biologists and medical doctors and decided to build such a machine. And the result is this one, our Gantry 1, which is, as far as I know, the first implementation of this pencil beam scanning worldwide. So you have here a schema of the beam line. Everything that is green can rotate, and what you see in the photo is just this part here. This part, there is one. The beam comes from here, gets directed out of the beam line, then parallel to the original axis. We have the scanning magnet here, and then a 19-degree magnet, which is under this big cover, that bends the beam towards the patient. We have the nozzle. We have the nozzle where we have this range shifter that I explained. It's a system of 40 plates of 5 millimeter polyethylene plastic that we can move pneumatically into the beam line. We have detectors, the dose monitors, and also position sensitive detectors. This is here the nozzle, and the beam comes out of this slit. Gantry 1 can do the scanning in only one dimension. We found that this is already complicated enough for the first machine, so we do the second dimension by moving the patient table. And the patient started in 1996, and for 12 years, this was the only spot scanning gantry worldwide. GSI in Germany, they also started a particle therapy program with protons and heavy ions. And they also use a scanning which is a little bit different from our scanning. We switch the beam off between the spots, whereas they do raster scanning, which means they do one spot and then very quickly move the beam without switching it off. So it's a slightly different technique. And this is why I can say for 12 years we were the only pencil beam scanning gantry. But they were also pioneers just a little bit later than we. So here's a statistic of the installed gantries. In blue, gantries that use the scattering technique, and in red, gantries that use the scanning technique. So there was a system here which had, I think, 3 gantries for scattering. This is Loma Linda in California, near Los Angeles. 96, our Gantry 1, and for 12 years alone. And around this time, commercial machines became available. If you have the money, you can buy such a machine. You don't need a physics institute to develop it. And you see from that point on, really, the scanning gantries took over. And here you see nowadays, this is 2018, but the trend continued. Nowadays, a new center, most of them want this scanning technology. So what we started 25 years ago has become the standard, and we are a little bit proud about it. So after a couple of years with Gantry 1, we thought, what would we improve from the experience that we gained with the first machine? And we constructed the second gantry, which you see here in this animation. On the patient table is just a phantom, a measurement device, but this is where we position the patient. And it has a lot of improvements. Some have to do with the clinical workflow, with the access to the patient during the treatment in gantry 1, depending on the treatment angle, sometimes the patient was 2 or 3 meters above the ground. And this made us always a little bit uncomfortable. If there is some problem, you have to reach to the patient and you first have to climb up there. So gantry 2 is designed in a way that you always can easily access the patient. But more interestingly, we also improved a lot on the scanning technique, especially we put a lot of effort in making the scanning faster. And fast is important not only to reduce the treatment time, which is typically a couple of minutes, depend on the volume of the tumor, but a couple of minutes. But scanning speed is important if you want to treat moving targets. A tumor in the brain is always fixed, but if you have a tumor in the pelvis and the patient breathes, it can move a few centimeters. And this is a problem for spot scanning, because then you don't have this precision, which is the advantage of protons. But if you are fast enough, there are ways to compensate for this organ motion. Some impressions how such a gantry is constructed. It's really, it's heavy mechanical engineering, because you need to carry these heavy magnets and you want high precision. You don't want that the whole thing bends, so it has to be massive steel. This is the 90-degree magnet of gantry 2, the biggest one. Here it is mounted, here's assembled. You see the vacuum chamber and the black thing. This is a measurement device, a CCD camera to check beam profiles and beam positions. Then we make the room look a little bit nicer for our patient. And in 2013, we treated the first patient on gantry 2. One focus of the of proton therapy is the treatment of small children, because in a child it is even more important than in an adult that you only hit the tumor and do not damage the surrounding tissue of the growing organism. And the complication with children is that they have to keep quiet during the treatment, and they don't like it. Adults sometimes also don't like it, but you can explain them. But children not. The smallest child that we treated was 8 months, so really they cannot understand it. So you have to treat them in anesthesia. It's a sedation, it's not really anesthesia. They still breathe spontaneously, that's the big difference. But still, it's an additional complication in the whole logistics. So we work together with the Children's Hospital in Zurich. They sent us a mobile anesthesia team to PSI. They start the anesthesia in the presence of the parents. Once the child is asleep, it's positioned on the treatment bed, then brought into the treatment room. This child here is lying on the back, has the head fixed by a bite block in the mouth. The bite block is fixed to the table. And the critical thing for the anesthesiologist is that they cannot be next to their patient during the treatment. They have to be outside of the treatment room. So they have to rely on their anesthesia monitors that send the vital signs outside, and they are just outside of the treatment room and watch what's going on. Very unusual situation, but we now treated almost 1,000 child patients like this, and luckily no accident, and the doctors now, they are also confident with this technique. After the treatment, the child is brought into a recovery room where it then wakes up, and then the parents can be present. Some words on the technology of the scanning. This is what was our goal for gantry 2. So we have this discrete spot scanning that I described in this animation earlier in my talk, where you go spot by spot, like in an old TV picture, compose the three-dimensional volume. But what gantry 2 can do is what we call line scanning. You move along the tumor, but you do not stop. You continuously move along the contour of the tumor. And this is a gain in speed. And there is something in addition to that what we can do. We have, from the gantry control system, we have access to the center of the cyclotron. In the center of the cyclotron, This here is the ion source. The protons come out here. They start doing their turn in the cyclotron. And here we have what we call the deflector plate. There we can apply high voltage, 1 kilovolt. And if you apply high positive voltage here, the protons are stopped because they see the positive voltage, they don't continue. Now, high voltage is something you can regulate very quickly. So this is a way where you can change the intensity of the proton beam quickly. There's a direct link from the scanning system on the gantry to the power supply of this deflector plate in the cyclotron. And this feedback loop allows us to very quickly change the intensity. So while we do the scanning, this here's an example where we just move the beam along one line. And we change this deflector plate voltage, and we see that the intensity vanishes. And here we do certain discrete steps. So this is a way where we have even one more degree of freedom that we can vary during the treatment. And this is all quite tricky and quite challenging from the point of view of electronics and controls, but it's interesting. So if you want to see more about PSI, during the pandemic, I did a video because we could not welcome visitors at PSI. So if you search in YouTube for PSI proton therapy, you will find a video where I give a tour of our facility and also a tour in the cyclotron bunker, which normally you cannot visit with guests. You can check that out. Now let me come to the last part of my talk. And I expect many of you have heard this word flash already. This is a new, I think it started 2018. So already some years, but still a very hot topic in radiotherapy. Not only protons. The meaning is the following. Normally radiobiology says what is important for the effect of a treatment is the dose. How much protons, how much photons do you give? But FLASH says it's not only the dose that counts. It's also how fast you apply it. If you do it very, very fast, like a factor of 1,000 faster, with higher intensity faster, you get a better sparing of the healthy tissue. So this effect that protons have built in is even enhanced. And there was a group in Paris. They started this here. You have always the reference in the slides. And I believe the slides will be available to you after this presentation, so you can check out these references. This is just an example with cells with electrons. You have the control sample, not irradiated. You have a sample irradiated with normal dose rate, and the dark color means there is damage in the cells. And then you have the same dose, but with a higher dose rate, much higher dose rate, and it looks almost like the not irradiated sample. So that's interesting. Why is this? CHUV is a hospital in Switzerland. Some people from the Paris group moved to CHUV, and they continued doing these experiments with electron beams. And also here you have on the upper part irradiation with electrons, a certain dose, normal rate, flash rate. With the normal rate, you see these black spots, and this is necrosis. This is something you do not want. It's an unwanted side effect in radiotherapy. So here you do damage to the cells, but here not. So interesting. They even treated quite early, this group in Lausanne, a human patient with a flash electron treatment, and you see the result after 5 months is really good. Now the big question is this also true for protons? These were all electron elements. And there's a lot of interest, was immediately a lot of interest from the commercial vendors of proton therapy facilities, because if you can treat with flash dose rates, you can treat patients more quickly, means you can treat more patients in one day, means you can make more money. So there's a lot of interest. And and all the important vendors, they started experiments at IBA here and Varian, even now the clinical trials. And this here is a result from Dresden, which is an IBA facility. Let's not go too much into detail. If there is a flash effect with protons, you should see a difference between these two curves, or a difference between these two curves, and you don't see a difference. So question mark is no flash effect for protons. So the answer is more experiments required. This was published in 2019. End of 2018, Gantry 1, our management had decided this machine is old, it's still working very well, but we would need to upgrade especially all the electronics because it was 25 years old electronics, no spare parts available anymore. So for clinical operation, this was quite a risk. It was decided that we should shut down Gantry 1 and do the clinical program with the two other gantries, which would be enough. So Gantry 1 was sitting there and everything switched off. And then our boss heard about the flash, and then he came and said, can we do flash with Gantry 1? We said, yeah, let's take a look. Now, I'm coming back to this picture with the degrader. So the degrader is there to reduce the energy. And when you do that, the beam gets spread out and you lose a lot of protons. They go left and right with the wrong energy. So when you go to very low energies, you have a very bad transmission of the beamline. When you go to high energies, you can get almost 100% through. Now I forgot, do I have this graph? No, I have to explain it here. So in order to, and this means you get quite a range in intensity in the treatment room. And this is something which you do not like because you have detectors that work well in a certain range, the dose monitors. But if you have a factor 1000 variation in the intensity, you don't like that. So what we do is we operate the cyclotron at a certain intensity. For the high energies where we get a good beam transmission, we on purpose defocus these magnets here. So we get an artificially bad transmission. And then for the low energies, we focus them and we ramp the cyclotron up to the maximum current it can give. And then even with the bad transmission, we get more or less the same intensity in the treatment room. Now we said, what if we open the degrader completely and ramp the cyclotron up and we focus the quadrupoles? Then we should be able to get the full intensity of the cyclotron into the treatment room. And we did some first experiments in late 2019. See here, this was November 2019. And the important number, this is a measurement from profile monitors on the gantry, already very close to the patient table. The cyclotron current was very low, 0.2 nanoampere. And you see what we measure here. It's almost 0.2 nanoampere, which means 100% beam transmission. And our cyclotron can go up to about 1000, or I say 800 nanoampere in stable operation. And if we go from 0.2 to 800, we get into the flash regime. So technically possible. Then we did, in January 2020, we did the first experiment where we put a scintillator block here. The protons come from here. We have a Faraday cup to cross-check the dose measurement. And actually, we measured dose rays of up to 9,000 gray per second. So yes, we are really in the flash regime. We were very happy. But this was January 2020. Then COVID came, everything stopped, sort of. Did I skip one slide? Yeah, this one. So later in the year, in 2020 and then in 21, we were able to do the experiments that we wanted to do with the flash experiments. We took zebrafish eggs and irradiate them the same dose, once with flash, once not with flash, and try to see if there is a difference. So this is Gantry 1. You see now it looks like a laboratory. And we are really very lucky because most facilities that do flash experiments, they can do this in the night and they have to change some things to do flash, but in the morning they have to put everything back because the patients are coming and everything must be perfect again. we have here a full playground for physicists. We can do everything we want. We can do all the changes. If we are tired, we go home. We don't need to clean up. It's really fantastic. And here are these are Marie-Catherine Wozniak from Lausanne. She's leading the team of radiobiology there. So she provided the zebrafish eggs, and we prepared such frames. And you see we have here these Eppendorf tubes where we put a few eggs. And this is then mounted on the former patient table of gantry 1. And you see in this frame we have 20 samples. And the table is motorized because we used it to move the patients. So we prepare a whole frame and then close the area. And then we can treat very quickly 20 samples within 2 minutes with varying the dose rate, varying the dose, whatever we want. In Lausanne, where they have the electron flash experiments, they have to position one sample with the laser, then go out, close the door, one sample, go back, take the next one, align again. So it takes a lot of time, and we can do this very quickly. So it's really very good because we benefit from the existing infrastructure in gantry 1. Yeah, and this is then our control room where we do the treatments, and after we take the frames out and then do the analysis. I have to go a little bit faster now. And we have results from these experiments, but they're not so easy to understand. And I see, for me, it's a discovery. It's really, this is biology. And there are many, many factors, and it's much more complicated than physics. I like physics more. I can understand better. These are these embryos after a couple of days, I think, growing. And if the embryo is straight, it's a good sign. If it is curved, it's a bad sign. And you have here the control sample, so it's straight. You have a treatment with photons. And you see this is here deformed. You have a treatment with electrons. This is conventional dose rate, and this is flash dose rate. And is there a difference? Hard to say. And here, protons from our measurement, is there a difference? Well, maybe this is a little bit more curved than this one, but it's very difficult to say something. So the biologists, you see again the reference there, it's published. They do the analysis quantitatively. Let's just focus on this picture here. You have the control sample, so no effect. You have the photons, you get a strong damage. When you look at the electrons here, you have to compare this red column with these two others. It's a little bit better with flash. And protons, this is conventional, and this is flash, almost no difference. What does this mean? So we said we need to do experiments with real animals. So we started a session with mice. We position them. This is the left picture is Lausanne. This is the electron accelerator, and this here is PSI with protons. We have a copper block with a small hole inside as a collimator, and then just place we irradiate the brain of the mouse to see for neurological damage. And I have to skip this because this is how we validate if the mouse has shows neurological damage. So photos from these experiments, the mice are anesthetized so that they don't run away. We position them and then do the treatment. So the neurocognitive response, how much brain damage you create with these treatments, control sample, photons, quite a lot of damage, flash electrons, quite good. So there seems to be a clear effect. And then the proton sample, yeah, there is a little effect. This star means it's 1 sigma, but we want more than 1 sigma for a real clear effect. So we were asking ourselves, a mouse brain is small. Maybe we do not always hit the mouse brain. Maybe we shoot on the side and then we don't really get an effect. So what can we do to check if we really irradiate the brain? And the answer is we need a PET-CT for the mouse to check after the treatment if the brain has been irradiated. And luckily in PSI, somebody had a PET-CT that can be used for laboratory animals. So we invited them to join us. So this is the PET-CT. It's a commercial device. You can move it around the computer with the analysis. And here is the PET-CT where you first, immediately after the irradiation, you take a PET image. And from the proton treatment, the irradiated part get a little bit activated. You measure this activation. And then the mouse is continued to make a normal CT. And because you know the geometry, then you can reference the activated image with the skeleton and you know where the brain is. And this is one of the animals here in the PET-CT. And this is a result. And if you look at the top line here, this was the first series of experiments that we did. And if you see here and here, we irradiate quite a lot the shoulders and not really the brain itself. So we improved the positioning of the mice. Improving the positioning means we taped their head with Scotch tape on the collimator. And then did the same, and you see it's much better. Huh? We really put the dose on the brain. So I think this is fantastic. This is physicists and electronics and software engineers working together to make this scanning device. Then you have the biologists that come in with all these cell experiments and their expertise on radiobiology. And then you get this imaging in order to make these experiments really work correctly. So this is really very nice way to work together with different disciplines. This series has not yet been published, so I cannot talk about the results. But this concludes my presentation here on proton therapy. So you see here, this is part of our team, and this is just what I described. Different people from different backgrounds, different ways of thinking, working together because we have a common goal. We want the best benefit for our patients, and this is really very big satisfaction. Thank you very much.
Thank you, Martin. So yesterday we listened about electron and what we're going to use electron for, like a synchrotron light or free electron laser. And today we hear from Martin as the beginning of the day how we're going to use proton. Thank you very much, Martin. And we have some time, right? Maybe for some questions. Okay, please.
Thank you very much for the very nice talk. Like that covers an entire journey of developing tools, and that was like a really fun ride. So for proton therapy, when you show the calibration curve, that looks really awesome, but also really scary because like the penetration would also depend on the electrodynamic responses of the each part of the body too, right? I guess this is not very relevant when you talk about the eyes, but when you talk about other parts of the body that can have varying dielectric constant, how much does the effective range of the proton change when you use it to kill tumors?
You mean this curve?
Yes.
Okay. Well, the range of the protons change according to what kind of tissue is transversed, if it's bones or muscles, or it's different. And this is part of the treatment planning. We make a sort of a three-dimensional model of our patient based on CT information. Okay, of course, I talk all the time that photons are different from protons, but you can relate. From the Hounsfield units of the photons, you can convert this, if you have calibrated your CT, into the different range of the protons. And then you adapt the proton energy so that you compensate for any changes in the range, so you're sure to cover only the target volume. This is a whole field of medical physics, this treatment planning, how you do this correctly.
I see. Really cool. Thank you. And one more quick question. So you said that each patient needs the collimator to be designed based on the shape of their tumor, right? What is the material of the collimator and how large is it? Like, is it the eye socket side?
Yeah, let me bring the picture. We use copper because you need just material with a certain density to stop the protons. But copper, the isotopes that get produced during the irradiation, they are short-lived. So after 2 weeks, there's nothing that is radioactive anymore, and you can recycle the copper. And the size is more or less 1-to-1 the size of the tumor. So for the eyes, they are like this. But if you can do this kind of technique also for larger tumors, but then these collimators get large. And this means that the radiotherapy personnel, they have to manipulate these heavy collimators, and all the time they are touching material that is a little bit radioactive after the treatment. So these are all, this is another advantage why if you can do the magnetic scanning, you don't need this and you don't cause this kind of worries for the personnel. Yeah.
I see. Thank you very much.
Discussion time after the
So I
morning
have
session.
two short question about the beam scanning for transverse direction. This you use magnetic scanning.
Yes?
Okay. Do you suffer from hysteresis?
Yes. We have to take this into account.
Okay.
Yeah. We always go in a certain way.
So you cannot do it very fast, right? When you have to reverse the direction.
We take this into account.
Okay.
We take this into account. We do actually something which we call teaching.
Okay.
Before we treat the patient, we run, we measure the beam position, we see it's a little bit wrong because of the hysteresis, and then we overshoot so that we get the correct position. And then you can do it fast. You compensate for this effect. You have to do it always in the same way for one patient, but the plan does not change typically during the whole treatment of 6 weeks on the gantry. So what you have to do this teaching once, compensate for the hysteresis, and then you can use it and still be fast.
Okay. For deposit the beam into different depth, you use the beam.
The range shifter?
Yeah. So and that would suffer from the beam stacking, energy stacking.
Yes.
And
That's-
how much the depth that can. What is the maximum depth that you can use as techniques?
Yeah. So the range shifter, which I described, this is gantry 1. This has 20 plates of 5 millimeter polyethylene, and it has about density 1, so 10 centimeters. So gantry 1 had used a few fixed beam energies and then do the fine modulation with this range shifter. Gantry 2, we can change the energy along the whole beam line. We move the degrader and we set all the magnets along the beam line according to the slightly changed energy. And we can do one energy step, which means 5 millimeter in the patient, in 80 milliseconds, which is very fast. And compensating the hysteresis along the beam line, you always come before you treat, you ramp the whole beam line to a maximum, you ramp the whole beam line to minimum, and then you go slowly up. So it's always in the same way.
Okay, thank
So
you.
we can do that with the beam line.
I'm just have the question related to the FAT experiment, the FAT therapy. Yes, because you talk about the comparisons between electrons and proton. And my question is, how do they find this is FAT conditions? Because there are a number that you say that, okay, this is conventional, this is FAT. And how do we know that this is already FAT, or it's that in between FAT and conventional?
Well, this is defined by the dose rate, and the dose rates, they were on the slides. It's a few centigrade, or it's a few
Where
hundred
are
or
they
thousand
come
grade.
from?
This is the difference, flash and conventional.
Yes. And where are they come from? From the experiment results or from some theory, something like that? Where are they come from, this number? Experiment base. I'm not sure.
Where, how?
Because, you know,
how we
like-
know the dose rate? You mean?
Yes. How do
We
you
measure,
know that
we-
it will have like fat conditions?
Yeah,
already?
we measure the dose rate. We have the dose monitors, and we know how much time we need to apply a certain dose, and this gives us the dose rate.
And you say that now you have fat condition because you do the experiment as well, right?
Mhm.
So maybe I formulate my question a little bit. So this number come from the experiment. If you have the dose less higher than this number, and then
Yeah.
you call this is fat.
Yes.
Right.
Yeah.
So you
yeah.
see, you get a number when you do the experiment, and it show the fat
Yes. Yeah.
results.
We measure it. We measure it ourselves.
I
Yeah.
see. Okay.
And there now slowly publications are coming out. It seems a little bit that the flash effect is not so strong with protons, but maybe this is because protons are already very good. Maybe. But
Maybe you don't need fat for proton, right? Okay. Thank you very much.
Okay.
I have a question about scattering and scanning systems. You said you change or you improve the speed of scanning magnets, and then you will compensate the moving of the organ. Is that right? And do you have a plan to replace, or to get into moving organ cancer using or utilizing scanning instead of scattering?
Yes, we not only have a plan, we are treating moving organs. We treat lung cancer, we treat other types of cancer using techniques of organ motion compensation that is possible with this fast scanning. It's now maybe not enough time to explain this, but one way is you give, say, 10% of the dose and repeat it 10 times. Then you get the same dose. But because you repeat it, the motion will wash out the dose inhomogeneities. This is one technique to do that. But
In the future,
it's a whole field. I cannot cover it in 1 minute.
then in the future, scattering system can be reduced utilization probably.
Yeah, we think that scanning has clearly advantages over scattering.
Because
Yeah.
scattering lost a lot of beam, right?
Mhm.
And you also have a beam spread of energy.
Exactly.
That's a
Yeah.
problem.
Exactly.
So thank you very much.